Sorry about that. I think now we can start. Okay. All right. So again, welcome back to the second lecture. Here we will discuss about the so like थोड़ा सा नीचे करो अभी ठीक है अभी ठीक okay fine. So welcome back again to the lectures on astronomical spectroscopy. In this lecture, we will look at the rotation is used in spectroscopy. So I'll be focusing mainly on the electronic terms, because I'm just slightly different, which will probably we discuss later, since I'm talking only about the atoms. The notations are simple representations, which will tell you at what state the electron is, and which will contain all the information about its state in sublevels. And that way you can easily identify its angular momentums, whether it is now, short mountain, or would be gravitum, and so on. So it's a very general representation, which we will talk about that. There will be going to be selection rules. As I said, all transitions are not allowed. There are some specific rules by which you can have a transition from one state to the other. That also depends upon the quantum numbers and the state in which the electron is currently at. Okay. So we will go to that one by one, and then I will try to do some problems during the course itself and see problem in the sense how does notation comes. So we'll do one example. So the quantum state of an electron can be represented by the quantum numbers. So the idea of quantum number itself is to represent the state of an electron. And we know that by Pauli's exclusion principle, all three electrons will have the same state, which means at least one of the quantum numbers should be different. So by looking at the quantum numbers, we can say, the state of the electron, and also two electrons will not have the same set of quantum numbers. That we already work. So when we can see that we represented that principal quantum number N, and the angular quantum number, and the spin, which is the intrinsic angular quantum number. Then we use J, which is the total angular quantum number. And in that, when you study even J, you may not rank some of the or yes quantum numbers, but J contains both M and S. Okay, so that also you will see later. So suppose you take one electron system. How do you represent that? So non-electron, which means the spin and the quantum number has a value half, that is near. The value SL can be 0, 1, 2, 3, and so on, depending on the value of M. So the J, which is the total angular momentum, is given by L plus or minus half. Okay? But J cannot be weight. That is the restriction. So if you have a atom 0 and one electron with spin half, so 0 and minus half is not allowed. It should be plus half. Okay? Okay. So now this table, let's say, represent a one electron system. But if you look at this, we have one electron, so S is always half. And then can have the N value, like depends when the electron is in terms of the N and T. So, and these letters S, P, D, F represent these sublevels, depending upon the orbital quantum number. If it is 0, you call it S orbital, basically spherical. A orbital is either the one, dumbbell shape, and then double dumbbell shape, and so on. And it goes to D, and it goes on like that. So how do you find J? It's straightforward. You have A squared minus half, and as they said, you cannot have A 0 minus half is not allowed, so it is half. Here, n equal to 1, so 1 minus half is allowed. Half, the 1 plus half is allowed, that is 3 by 10. N equal to 2, 2 plus half is 5 by 2, 3 minus half is 3 by 2. So these are the values possible. Okay? Yeah. And there is something called multiplicity, which is 2s plus 1. And I didn't capital S because that corresponds to the total spin of the electron, capital S. And this is, say, S is half, so 2s plus 1 is 2. So here's how you normally write. First, you take the value, the letter corresponding to the L, say S, so you write S, then you write the multiplicity, so 2, and then you write the J value, which is half. And it is pronounced as doublet S half. So this is called a doublet state. So whenever you have S is equal to 2, 2s plus 1 equal to 2, that is multiplicity 2, it's called doublet. So doublet S half, doublet E3 half, doublet E half, doublet V5 half, and doublet V half. So this is how you normally write the spectroscopic notation for an electron. Now suppose if you have more than one electron, then how do you do it? Okay. Now, when you have more than one electron, you can't directly write the spectroscopic notation because it is going to be a combined notation, right? So then the spin will change, the angular momentum will change depending upon the NMS. Now, here you need to consider NS coupling. Okay? Now, there are two types of couplings. I'm going to discuss only one at this moment. Okay? The rest, you can look at it. It's not very difficult. There is NS coupling, and NS is, and it's for angular momentum, S is for spin angular momentum, but I mean, somehow, coincidentally, and SN and so on plus 1S, so it is not RS coupling, okay? It is NS coupling. So SN and so on, they were option on us, basically they came up with this idea of, doing. Now, NS coupling is applied when the spin-spin interaction, okay, so suppose there are 2 electrons, so this is for more than 1 electron. So now there are 2 electrons, and the electron moves spins, right? Up and down, you call it. And you present by up or down. And the spin coordination is much more than the interaction between spin angular momentum and orbital angular momentum. When space spin is used in orbit coupling, then you use LS interaction. What I mean to say is, say suppose spin is very strong, right? So suppose you have S1, then you have S2, spin electrons, right? And the same electron will have L1 and A. Okay? You write it in small letters. Well, I'm saying that space-spin coordination is important. It means this interaction is going to be stronger than this interaction. Okay, so when spin interaction is stronger, the must first look at N. So you need to find out S, which is equal to S1 plus S2. Okay, so you need to look at this first. You need to get the total spin. And then you should get I equal to L1 plus L2. And writing this, because it's not a vector and putting it, because you can have plus and minus in both directions. Okay? So that's why I'm putting it, or number you can put in minus S, but you usually put it in this form. So first what you're doing, you find out the totalness, and then we're finding capital L, and this is called S coupling. So you find capital S with an L, and then couple them together, and this will give you capital J. Then you combine N and S to get the capital J. And this is called the essence on the LS coupling. Now the other coupling is it's called JJ coupling. Okay. So where you can see that I'm writing small j. For JJ coupling, you write small j. The reason is simple. You'll understand what I'm saying. I'm going to say now. This is a case when you have S1, S2, L1, L2. While this interaction is clearer than this particular interaction. So, this is clearer. So, when you have a spin-orbit coupling stronger than space-spin correlation, then you use JJ coupling. So, how do you do that? So, for each electron, so for the first electron, this is for second electron, and so on, is tied J1. We'll find J2. This is S1 plus or minus L1, S1 plus or minus L2. Okay, L2. S2 plus or minus L2. So, in this case, what you are actually finding out, we are suddenly all the S and M of each electron, taking the J, totally independent for each electron, right? So, for the first electron, we get J1, second electron, we get J2, and when we find J is J1 plus J. Okay? So, that is why it is written as JJ coupling, because you are coupling with J and J, which is you are finding all the J for each electron and then you combine them. But in the previous case, in this case, it is you add all the spin, get the total spin angular heading, you add the orbital angular heading, that is L, and get the total angular heading, and then you combine both L and S and you get the LS coupling scheme. Is that clear? So condition what? If the spin-spin correlation is stronger than spin-orbit coupling, then you use LS coupling scheme. But if the spin-orbit interaction is stronger than spin-spin correlation, you use JJ coupling scheme. Now the problem with, if you generally look at the elemental structure, it's like smaller atoms, elements, you usually use LS coupling, and larger atoms, you usually use JJ coupling. And if you ask me where is the boundary, it's very difficult to say. We see that somewhere at the region, and both may not be exactly this equal, and there will be some slight variation between the two. So it's not like there is a clear boundary, like from here onwards you can use this and so on. No, it's not there. Okay. So in that case, you'll have to use the best approximation, best scheme, MS or JJ for that element.
Is that specific reason for this?
Yeah, that's the reason is the interaction between them, right? So for example, you're talking about the spin and spin interaction is very strong. Very strong means in the total Hamiltonian, right? If you look at it as a potential, the spin-spin term will be very stronger than the spin orbit. Right. So the spin-spin you need to initially combine it. Oh, you're talking about, okay. But when you have very high, angular moment, very heavy, the angular moment is going to be very high. And there will be loss, and then they are going to interact much stronger with the spin. Okay, than the one with the elements. It's called it.
And so when you're suggesting that maybe when we have to choose between JJ or 2M, so how do we choose which one should be?
Well, that's something which is not very clear. In general, you will have a specific, right? But the idea is that, one shouldn't see that. See, you can do JJ coupling in both schemes, right? And you get different results. Like the energy levels, when you look at it, you'll find that for the low atomic number elements, the LS coupling scheme will give a better representation than the JJ. And slow, it's a very slow transition. And then there will be a merging in between. It will merge and then it will go back to the JJ. So we can see that at one point, they will come very close to each other. Okay, in the energy level diagram. The energy level diagram is different for both. So if you have an energy level diagram for LS coupling, you have an energy level diagram for the JJ coupling. For the low atomic number elements, you have the difference very clear. And this here you see that they come and overlap and then comes different. Something like that. Okay, that's why I said there is a clear, but woman where you said, okay, from here onwards you can use JJ and here onwards you can use LS. Okay, so now, so for a multi-electron system, how do you combine them? Okay, that's what we are going to look at now. So, how do you start with this? You have first, because it's a LS coupling, first you need to look at the spin. And remember, and the spin angle is coupled like this. So start from, you add S1 and S2, and you start from union 1, and then union plus 1, union plus 2, up to the S1 S2 maximum. But S cannot be negative. It can be 0, but it cannot be negative. So I think that's just meaningless. Okay? So you cannot have a negative value. The minimum should be 0, but actually is the sum of them. Okay? And once I'm telling you how to do that, I mean it's very difficult. At the way you have to look at the Y velocity is just 2s plus 1. The same definition. Okay? So now let's say you have one electron system, which you already know, right? S1 is half. So capital S is half. Okay, so this is okay. S is half. And the half ES plus 1, the multiplicity is T, and it's called a tablet. Okay? Well, suppose you have two electrons. S1 is half, S2 is half. Okay? So now the minimum is half length half. So they have 0, and then you are plus 1. Okay? In this case, that is the maximum as well. Sometimes it can go here than that. Okay? So, but in this case, the S1, the maximum is R plus half, that is 1. So, it goes from 0 to 1. So, 0 and 1. We see the next case, it will go much better than that. Now, what is in the T? For S is equal to 0, it is 1. That is called singlet. Then for S is equal to 1, it is 3. That's called a triplet. Okay? Now, for 3 electrons, how do you do it? So I put a bracket here, which means you take this first. And then the total spin. And then you add it to the S3. So this still you have already done here, right? You get 0 and 1. And then your S3 is half. Well, you need to add this. So how do you do it? Take 0 and half. 0 and half means you can have S half. Minus half is what about? 0, 1. Then you have 1. Right then, 1 minus half is half, and 1 plus half is 3 half. So there are 3 years, half, half, and 3 half. Okay? Once there are different such states for the spin and union. So the multiplicity is 3, 2, and 4. That is, keep the bits and a quartet. Okay? When 2s plus means 4, you call it quartet. And if it's 5, you call it quintet and so on. Okay? So this is how you add the spin. Clear? Okay. Now, we take the and orbital angular momentum. Then we need to add all the orbital angular momentums. And the same N1 plus N2 V1, N1 plus 1, and T up to N1 plus L2 maximum. Okay? Well, now there is one more thing you should learn. Clarity. you should also have something called parity. Parity means L1 plus L2 is odd, means odd parity. L1 plus L2 is even parity. And this will also come into the spectroscopic notation. Okay. Now, let's take the electrons. Okay. In this case, you will mention in which, well, level they are, some levels they are. So, one electron in 8P and one in 3D. Okay. So now, that is L1 is A. Aliens, V. Right. SPVF. Going there, right? So it goes like S. Oh, I have written R. It's SPDFG, right? So S is for the n equal to 0, n equal to 1, n equal to 2, and so on. Okay? So, yeah, N1, right. And then go to 1, and it will go to 3. Now we need to combine this. Okay. That is 2 because it is a V orbital. When V, n equal to 2. Okay, because 0, 1, and 2. Okay. Now, so 1 and 2, well, how do you combine this? You have sin n minus 1. Very, very simple you can get, right? Then there is you got as 1 or 1 minus 2. Minus 1 and plus 1. That is more or less, so the minimum is 1. And the maximum, 1 plus 2 is 3. So it's often 1 up to 3 with a max increase of 1. So 1, 2, and 3. So aiming out the combinations. Okay. Parity. Parity is 1, B is 2, 2 plus 1 is 3, just odd. Right? Because this array none plus 2 is equal to 3. This is odd. And what are the states? It is written as, so it is, it depends on the L value, so PVF. The states will be PDF. And this is complete, we'll come to the that later. Now let's look at 3 electron system. Okay? So the same way we did, we had to combine this first. Okay? So T is n equal to 1, A is n equal to 2 equal to 1, B is 3 equal to 2. Okay? So you have the average results. First you need to combine these two. So 1 minus 1 is 0. So it can start from 0. And 1 plus 3 is 10. So it goes up to 2. So 0, 1, and 2. Then you need to combine with the third one. So for 0, then a 0 minus 2 or 2 minus 0 is 2. So we bring a value. Okay? So that is 10. When you take 1 and 2, and minimum is 1, maximum is 3. So 1, 2, 3. Then we take 2, and 2 minus 2 is 0, 2 plus 2 is 4. So 0, 1, 2, 3, 4. So it is the states for L. And you can see that there is 1 S, 1 TP, 1, there are 1 and 2, yeah, TP, 1, 2, 3, 3, you have and then G. Okay? Is that clear? Yes. All right. Okay. So, this is going to represent them. And then, you want to go a little bit further on this. The input. Sorry. Sorry about that. Okay, it's gone. Okay, good. Okay, so this is done. One more the J. Well, you need to find the J. Well, if you look at this joins A plus S and going up to L minus S, or reverse, L minus S going to L plus S. So let's take the PLP system, which we did just before, with 3P and 3D. And that, if you look at, we had this you have S is equal to 0 and 1, and N is 1, 2, 3. Okay, so that's it. S is 0 and 1, N is 1, 2, 3. So now we need to find J. Okay, so to find J, first we need to look at, take the first one, S is equal to 0. For S is equal to 0, what are the J possible? S 0 can combine with 1, 2, and 3. Right? So not either is J 0, 1, 2, 3, because it's adding to 0. We cannot have negative, so it is 1, 2, 3 itself. Okay? So that's the first case. Then we have S is equal to 1. Now S is equal to 1, combine with N equal to 1. So you can start from 0, and then 1 plus 1 is 2. So 0, 1. Then S is equal to 1, N is equal to 2. 3 minus 1 is 1. 3 plus 1 is 3. So you can't go from 1, 2, and 3. When S is equal to 1, N equal to 3. So 3 minus 1 is 2. 3 plus 1 is 4. 2, 3, 4. So what we have is 1, 2, 3, 4, 5, 6, 7, 8, 9 set. But of course, this is for N equal to 1, N equal to 2, N equal to 3. Okay? So now how do you, and then of course, you will look at the parity, the multiplicity. S is equal to 0, it is 1. S is equal to 1, 2s plus 1 is 3. So that is 3. Parity, I is, you have to look at the electron. E is 1, B is 2, so it is 3. So it is odd. Okay, and then plus value 2 is 3. Okay, so now, how do you write it? So, that we know is, okay, I think, let's take the first case. So, what we know is N equal to 1, 2, 3. Right. So, I'm going to write for this case. I think there is the real case. So, N equal to 1, N equal to 2, and N equal to 3, which means we can have E, then A, and F. Right? What is the first one? Then, it is a singlet. It is singlet. So, we have to write a singlet. Then you have to look at J. Then in J, for N equal to 1, J equal to 1. For N equal to 2, J equal to 2. For N equal to 3, J equal to 3. Okay? So give a notation. And then what's the parity? Odd. You put a small dot or hand at the top. Parity is also very important. So this is the spectroscopic notation for N. S is equal to 0, that is a singlet state. Can you type in this? Yes. Parity is, so this is N1, right? And then why? Because it's a p orbital. This is L2, which is B, which is a 2. So N1 plus L2 is 3, which is odd. Okay? Can I doubt in this? Is it clear? Okay. Now, let's look at the next one for the triplet state. Okay? Now, for the triplet state, so I'm always again, this is N equal to 1, N equal to 2, N equal to 3. And it's a triplet state on parity. So here I'm going to provide this. I'm going to I can, so in this case, I'm not going to write for each j. Okay. So there is another combined way to write it. Okay. How do you do that? First, and you go to 1. That is p. And then it's a applet. So then, and there are the 0, 1, 2. And on parity. Okay. Now, because within the we the 3 different states, okay, substates. Okay, then confused that this is single state. It's not. It's that to make it simpler, you write it in this form. But they are separate because they have different J values. Whenever you have different J values, the sense the energy levels are different. So they are not the same state. Okay, so the electron can be of 0, 1, or 2. So, but we can write it in this form to make it easier to represent. And also similarly for any product V, it's a triplet and it's 1 to 10. And on parity, in the last one is equal to 3, that is off. It's a triplet, and then it's 2, 3, 4, 2, 3, 4. Okay. Is that clear? Fill it out. Can ask me now. Oh, good. Great. Okay. So, this is how you, so whenever you see some notation like this, like seeing that the 1, okay, then you should know which state it belongs to. Because you know it. It's a P state, it's a P means I'm equating 1. J is, that is why, what will be J value for this? 1. And it's a single. If it's a single, you should be the spin also. Right. Or if you have J, you have arrow, you can find this. Okay. Okay. Maybe before we go to the next one, we can do one example of the linear. Okay. So that's why I bought this book. Okay. So this is the atom. So excited germanium atom. Okay. I will do it here itself because I don't have a blank screen here. Okay. We'll use here this one. Okay. So an example. No. Okay, excited state for P for D. Okay, so there's the 2 electrons in the valency and they are in for P and for D. So it's an excited state. Okay, because 1 electron is in P, 1 electron in B means one of the electrons from P is going to the D. So that's an excited state. Okay, so how do I write it? What is S1? Half. S2 is equal to half. What is L1? 1. Then it's a p orbital. Right? And what is L2? 2. Oh. Okay? Yeah. Did we do the same thing? Okay, probably it looks the same, but anyway. Now, so first, since it's the AS coupling, we need to write the value of S we get. What are the values of S? Half minus half is 0, so it stands in 0. And half plus half is 1. So S is 0 and 1. Okay, what are the BI? Or okay, so let's write what is 2S plus 1? 1 and E. So it says singlet or triplet states. Okay. Now, L. That applies when you L values. It should start from the beginning, just bring that as 1. 1, 5 seconds, 3. So this one, right? 1, in, and 3. And this corresponds to in, B, F. Okay? This is important because the spectroscopic notation that is represented by the L value. Okay? So it is PDF. Okay? Now, the next is summation number L. Which is the, of course, here it's only 2 electrons. So the equality is usually represented by this. Okay? So it is 1 and so this summation number L is 1 plus 2, which is 3, and this is odd parity. Okay? 1 plus 2 is odd parity. Okay? Okay, so now, but we have this cause we Syrian case. Okay, so the Syrian case, what we have is as if we going to 0, and you can combine with this, so it is 1, 2, 3. So it will be 1, 2, 3. The same as what we just did, right? So it is, so F is equal to 0, I equal to 0, J equal to, sorry, N equal to 1. Yeah. So it is C and Y. Okay. Yeah. M is, okay, let's start with N equal to 1. Okay. So this is the first case. Now, so let's write down the spectroscopic term. N equal to 1 means P. And it is, it's a singlet. 1, that is with 0 on the 1. And it's then odd parity. Okay. So this is complete. 1 and equal to, for N, so this, maybe I'll write it here. N equal to 1, N equal to 2, or N equal to 2, and in the is it's a D, it's a singlet, and N per 0, that is T, and its parity is odd. And N equal to 3, it's a odd, it's a singlet, J is 3, and F is 0. Clear? Here the third case, that is S is equal to 1. Now when S is 1, okay, so what are the options we have? You can start with 0 and none, so it is 1. Sorry, 1 and S is none, sorry. 1 and 1, you can put 0 to 2. So 0 and 3, 3 means 0, 1 and 3. So, and it is where I equal to 1. It is and it is a 50, 7, 1 and 2, 3. For N equal to 2. Okay, and S is equal to 1. It stands from 1 to 3. It's a B, it's a equipment, so 1, and 3. And N equal to T, it's odd, liquid, and E plus 1 is 4, E minus 1 is 3. So this E, E, and O. Okay. So now, if you look at this state, Why do you call it triplet and singlet? I can see that there's got to be one state with one angle on them. But here, each of these states has three substates, sublevels. So that's why it's said that. Okay. Well, there is one more thing I think before we turn to the next part. If you look at how do you arrange the energy levels? I'll just be very detailed about that. And so when you go into the selection build, because I need to own that as well. So, the energy levels are arranged depending upon some variables. Okay. Now, yes, you bought all these states, but how do we arrange? Okay. The lowest energy level should be at the bottom, and then others will be above that level. So how do we are arranged? How do they are ordered? In the sense of then, two things. The first is then authorize. Okay. So I can very broadly explain because there is no theoretical way of reading it, and we don't have time for that. See, the spin, suppose you have 3 electrons, right? Let's say you are talking the 3 electron system. And we have 3 electrons, and the electrons, we know that this electron can have different states, should have different states. Suppose they are parallel to each other. That is a third state. Okay. So for a pure electron system, there is S1 equal to half, ST equal to half. So S can be 0 or 1, which means it can be a singlet or a triplet. Now, there are 3 electrons. So this they are anti-parallel to each other. Opposite spins. If they are opposite spin, it's a singlet. Right? Now, if they are opposite spinning, means they are different in terms of its orientation means. But there is explosion possible, doesn't have any problem between these 2 electrons. Okay? Which means there will be a compared to, of course, it's a comparison to the fifth case, which is this case. Because now they are the same dictate. Of course, other quantum number may be varying. It may be 2 and 4D. So this is allowed in principle, but in terms of spin, we are the same state, which means because of the exchange force, they will be pushed apart. Because they are now indistinguishable in terms of this spin. So they'll be pushed apart a bit. Okay? Well, then, so what you see is, since, and then now you have to talk in terms of its interaction, electron-electron interaction. So what I'm going to say here is the anti-parallel ones, because of sent from the standard state, the anti-parallel electrons will tend to be closer than parallel electrons that is a perfect. Okay? Now if you look at it, it's repulsion and attraction. So you can talk about in terms of repulsion. Which will be with more force? The first one. So this will be responded with much larger force because they are closer compared to this one. So the impulsive phase is less probably ordinary ones than the anti-parallel ones. Did you get the point? Yes. Because they are parallel, they tend to be closer than the anti-parallel one used to tend to be closer than the parallel ones because of the charge, the exchange potential. Okay, because of the indistinguishability. Since they are further, between M with and less than V, the one which is anti-parallel. Now, in that case, which means that this case will be more negative. I'm saying this will be less repulsive than this. So this will be require negative in terms of energy. Less repulsive. So this will be more negative, so this will be more negative energy than the anti-parallel case. Say, more negative energy means what? No stable, which means it can't will be beyond the singlet. So, if you look at the S is equal to 0, it will be here, S is equal to 1, it will be here. When you doubt in this, it's a very abstract when explaining it. Like, I would be quoted. You got this? Yes? All right. So this is that is M. What about the angular movement? Now, the angular movement is very simple to explain. Okay. Suppose you have two electrons, right? Moving around. These then moves. I'll show you. When we used every, they are exactly opposite, which means having the maximum angular momentum. Okay? So, you got it. So, you have the maximum momentum means less repulsive, more negative, and then over. Okay? So, that is where the values. So, which means higher the RDM number, the lower the energy is. Okay? Higher the RDM number, the lower the energy is, and it's still the lowest, and then we are at ring neck. Okay? So that is the orbital angular momentum. And then J, I'm making it a bit. Okay? So J, you like this. Okay? So J dot J is hydrolytic. How do you like J dot J? Okay? L dot N plus S dot S. Yes? Wise L dot S. Right? Okay? So the energy, so not like looking at J. J means speed of it thing. Right? The cup, how does it coupling? Okay? So we are looking at endless coupling. Well, one thing which I can't derive is memory is the energy change between the spin of line. And that can be derived from time-independent perturbation theory. Okay? So the delta E, that is the change in energy, is proportional to I dot S. Okay? So this is something you can derive it when you do time-dependent time-independent perturbation theory for spin orbit coupling. Okay? When you do that, you get this. Which you can find out from here. So that's what we need to find out, right? So here, any dot S is equal to half 0 dot J minus L dot N minus S dot S. Okay? Then what do you need to find out? Okay. So that is now we need to what we need to write is the eigenvalue of J square. J dot J is J square, right? What is the eigenvalue of j square unique? What is the eigenvalue of L square? Say, for example, this entry we need to do later. Say you have L square m. So this is one particular state with that value m. Say that is eigenvalue of L square. LMB, L plus 1, H square, and m. So this is an eigenvalue problem. Okay? So the eigenvalue of L square is L in the replacement H square is H square. Similarly, the eigenvalue of J square was J into J plus 1 H square. Okay? So what you can write is, well, okay. So what we want is the I dot S. So this can be written as half H square, and then we will have J into J plus 1 minus M into L plus 1 minus S into S plus 1. Okay? All the three angular momentums will have similar eigenvalue. J square will have J into J plus 1 H square. S will have S into S plus 1 H square, and so on. Okay? They are analogous to each other, and we'll have this particular value. And this is the delta S. And this we can write in the expectation value form, say it is the expectation value of the thing. And this is now we have put in terms of the value itself. Now you can simply say L dot S. So if you can find out and go to this value, that is proportional. We are not worried about the constant. This part is not worried. We are going to only have this part. How is this? Reply. Okay? Well, suppose we take the state. Okay. Well, we are trying to see how then the energy difference between these states and J states when vary are maybe placed. Okay. So now I'm going to remove this. So this is your delta E. If I wait there. Okay. Fine. So your delta E is proportional to J into J plus 1 minus M into L plus 1 minus S into S plus 1. Now I'm going to take two states. So one is delta A at J plus 1 minus delta Na of J. This delta E is the change in energy at argument on the thing. Okay. So I'm taking the delta J. So suppose you have two states. Okay. This is J plus 1 state and this is J state. I'm trying to find which is never and which one is that, right? This is then consecutive states. Okay. So I'm trying to find out the difference between these two. Well, you see, we got very good. Now, suppose let to say some constant, right? So it doesn't matter. So the constant will remain. This will be equal to some A. Now, what I'm going to do is, I'm going to keep N and S the same and only J will vary. Which means this we cancel it. Only subtract it. Okay. I take the same again and same S and try to find what or you put the difference when you have the two differences. So this will cancel out, and then what you got is A and B. Okay, so this is going to be J plus 1. This J is J plus 1, and this is J plus 1 plus 1. Then this is the J plus 1 state minus J in J plus 1. Correct? Say it is J plus 1 state minus J into J plus 1. Okay. If we simplify this, what do you get? This will be E O in J plus 1. So just simplify, you get this. So what it says is, it's a basically predicting the J plus 1. What it says is, take the consider the energy levels for J plus 1 will be the owner. This is proportional to J plus 1. And EA is a constant, it's a positive quantity, it's not negative. So, yes. So, what we have is the energy at the J plus 1 state. So, the J's will be the second. The larger of the two J's will be highest. Okay? So, then you take. So, higher the J, higher the K. So, in this case, we have higher the J, higher this. So, for this, then we have it below than the singlet. For M, higher angular momentum or energy, and for J, wherever the J, yet angular energy level. Okay. So these are the values which we rapidly use. We need and write down the energy levels. Now, this is called a normal triplet. Okay. So, normal means this is usually you'll see in most of the cases. That there are some cases when you have the number of electrons is half filled, right? For an atom or something, you see inverted, which means you'll see exactly reverse. Okay, so I think I'll learn nothing to that. So it's called inverted triplet. That means the J, whatever you said, will allows the higher the J, higher the state is. That then you can have an inverted one when now the system is half filled. The balance band is half filled. Okay, so I think that's so now making the thought in you. Oh, okay. I think probably we'll continue this a little bit more. Okay, because I need to. So maybe in that as an exercise, well, we have you can resolve variation now, and we did for Germany 34D just now. So in the exercise will be to draw the auxiliary diagram. First, so how do you do that? Again, it took something like this. So this is 30 D, and then right. So B is equal to 0. This is equal to 1. Then you split. I think it is a split into how many levels? 8. And this one split in the. Now, in this case, we need to write a bit. So this is for the this is for like D, and this is for the plug F. And this divided in D. It goes like this, right? Because in each that has the J values. So you need to add out them. Yep. But you can try out. Okay. We need to go and the selection rules. I'm going to skip this. This you try out. Okay, and there's the diagram. Okay. So okay. So having a view, I've seen this particular expression. I've seen this expression somewhere. Well, I'm a confession of your gone and very busy also. And this is Einstein coefficients. But this is the emission coefficient. What? This, probably. With what it's fine. It's in the perturbation theory, it's there. It's the things that I'm acting in an electromagnetic field. Okay? And this basically, then the transition probability of an electron empty by two approximation. Okay, the others, so because you can have key ones, and there is a penalty that this can transfer from P to N. Okay, that is given by this expression. And this bracket notation, everybody's aware of this bracket notation? Okay, so the bracket notation is nothing but this, right? Here and in that. So this is the transition probability that an electron means an electron will go from an P to 1 when this is true. Okay, which means these are linear constants, right? Einfeld, fine, structure constant, C, Pascal, they're all constants. So anything which is remaining is the one, the bracket notation. Bracket 2, this higher level, 3 more than level. So it's 20 to 1. So the minimum condition for area transition is this equation, or equal to 0. If that is 0, V to 1 is 0, probability is 0, so no transition occurs. Is that clear? Right? So this, the expression, I'm going to derive it, but you assume that that's correct. Okay, so now I can do some simple working this. Okay, so if you look at this computation making you already know, right? And next is the RH class 1, and zy is minus a equals x, and zz is equal to 0. And LZ is given by x in y ux, and ex in the object time is minus L cross del. Now, we can do this as an exercise to print this. Okay. It's not very difficult. You use a substitute and you should get. And what LZ means? It is IZ, Z minus Z, LZ. So that's the computation relation you already know. Well, let's take two levels. So that's what we have, these three levels. Okay, so I'm taking that level, M, the upper level, and N prime, L prime, M prime, the final level, will be the lower level. Okay, and the even is LZ, as the already made this as well. LZ, M is MH cross, and this is the kit, and this is the director, and Z is equal to N prime and prime H cross because it's coming out from the director. And there is U star because M the N number. So you need to complex conjugate it. Otherwise, you need to complex conjugate. You want to know that, right? Okay. So these things are. So let's take this, and this is the one equations. You know, the transition is basically 1 equal to 0, then this happens. And that is what they find the fact. So basically, and the non-zero means that transition is allowed, zero means not allowed. Like you know that NZ was it, which means that now we can write that the bucket notation with LZ is right inside. And you know that since it equals 0, it should be equal to 0. Because LZ is equal to 0, so in way you will have bracket notation is written 0. Here. Now if you split it, can get M to the N prime, L prime, M prime, and Z minus Z, LZ, and LM. And by doing that, we again or LZ, here edited is an M prime come out. From here, you get an M coming out, MH cross, and here M prime H cross. This is clear? From the director, M prime, and from the kit here, M. Well, you can take. So what is the common name? And this is common, right? So you have Z here, say M prime, I prime, M prime, Z, M not equal to 0 with this quantity. Click. Now, I know that this quantity will lead to 0 means web transition. Okay? Say this cannot be 0. And H causes is not equal to 0. So then you have is M prime minus N equals 0. Delta and equal to 0. This is an alive transition. Okay? Which means this is an alive transition because this cannot be 0. We started with this equation, so we get delta N equal to 0. So this is one of this selection rule. Delta M can be 0. And next one, take the other, so this is from the, for LZ, Z, we got this result, right? So he found down LZX and LZY, you get these two. So what you can see is, for the similar expression here, say with an X, right? Here, and prime minus N. And on the right hand side, then we have this IH cos, and the IH cos conjugate, then with a Y. And the second equation is LZY. LZY will be there, and fine with an I. And on the right hand side, minus IH cos X. So minus IH cos with an X will be bracket notation. Is that clear? Can we go ahead? Okay. So now, it is delta M. So I'm just writing it out, delta M. And then I'm taking this to the left and this to the right, so that it had X here and Y here. Then you can simply divide them. So there you have delta M by minus I is equal to I by delta M. Okay, so it's nothing like delta M square is minus I square, which is equal to 1. Say delta M is plus or minus 1. Okay, so this is the, so combining both delta M, that is M can change as 0 or plus or minus 1. So this is the first selection thing. Okay. Now, the second is for L, where I'm going to use this particular expression. Okay. So you can try to do, you can take the left hand side, and if you just do it, you should get right hand side. Okay, and blow it around. So I'm trying to do this, say, when it says, if you plan this, you should get this. It's all in terms of Z. So, and you know that I squared M is any equation which goes squared, and you use that, you get this term coming out, and then primary prime Z M. On the right hand side, you get Q epsilon squares raised to 4, I prime plus 1 plus M plus 1, and you get this. These two, I don't want to go it right now because it's literally long way, but assume that they are true. So now if you include with side, and we get the next semester get considered, and we get these two expressions. And you can simplify it by using this particular formula. You simplify it, and then you find that you get these two terms. Either I prime plus L plus 1 equal to plus or minus 1, or L prime minus L is plus or minus 1. And they're the two things you get, because it's score, right? Any of them can be 0. And you can see that if this is true, L will be negative. Okay? Because you cannot have L prime plus L equaling singular or 2. Okay? So you can see that this will become negative. So if this is not a Y, so what you have is delta 1 is plus or minus 1. What is the second array? What? This, he won't eat me either. The entire. This is angular momentum, right? And you know that when it goes from one state to the other, it will change that one angular momentum. Why? Photon has one angular momentum. Photon is not HU, right? Or H cross. It is one angular momentum. So when it goes from one state to the other, it has to absorb and emit one photon. One photon means one change angular momentum. So it has to be 1 plus or minus 1. So the change in angular momentum should be always V by T, whether it's plus or minus, because it is emitting only one photon from one particular transition. So you can simply say straight from here, have you never got an upper between stage 15 but unknown eternally, because photon has one unit angular momentum. Okay? So it's about, so well, using the selection way, how can you look at the transition? Okay, now another part, and there is the selection way for let's look on the name. Is there any? No, there is no selection rule. Okay, it can be from any step to the other, and you must show later. But next few lectures, I'm not going to talk about that right now. I'll simply show you that. So, suppose you take a particular system energy where it isn't like this. It is arbitrary on it because it's not. I'm doing this to look at separated, but the separation is not there. Okay, because this will be much higher and then smaller, but it's okay. Fine. The S means n equal to 0. This is E means n equal to 1. Yeah, D n equal to 2. Okay. So, what is the forward transition? Then, no taken the Z minus 1. So, but you see, I didn't know that there is an animation. Come back. Okay. Here, these are not allowed because this is S means n equal to 0, n equal to 0. Delta n equal to 0 is not allowed. And this is not allowed. This is not allowed. It needs the S integral because delta n is 3 now. This is 3 minus 0. And this is also not allowed. So we have more bit of transitions. Okay? This is not allowed. Now, what are the allowed ones? This is allowed because it's 1 minus 0 is 1. 1 minus 0 is the 1. 1 minus 0 is the 1. 0 to 1 is allowed because it's minus 1. And P is allowed because it's up. Okay. This is allowed. Okay. So these are the allowed transition. And of course, this is really very arbitrary quantum, right? These are the allowed ones. But what about the okay. So this is something you can exercise, you can try. Okay? Can you use another transition not even the 3 to the 2? Okay? Something like this. EL and EL prime prime. Okay? So, and then there's 1 0 to n minus 1, m n is minus 1. Let's say, and find all the allowed transitions. Okay? You can just have a look at it. And what you can tell in grade. Okay? So, I think that's probably the end of this lecture. If you have any doubt, you can ask me now in this. It was a little faster because I wanted to finish it and then we have some people else to do. So if you have any doubt regarding the part, you can ask me. Yes.
Yes. No doubt, but I want to add one thing.
Yeah.
At this rate that the pursuits are more stable than the signal.
Yeah. And I have not that stable. It's having a lower energy state than the other one. Yeah.
We can say that both the electrodes in engine state are in same orbital, so they are more closer. And
it's because basically one is a quantum and the is different. And I'm talking about both of them having the same spin and same A and same N. That is not allowed, right? So where it clearly says that the angular in one terminal will be different. They're having the same N. And the other way around. So for example, for P and for B, the N is the same. When the spin can be parallel or unparallel. Yeah. Because you can have the same with the same test fundamentation where in a Bruce Piley's calculation result should be not allow that. Yeah. Good. Anything else? If you have any question? If not, only break for 3 and then come back and then do some preparings. Great. Thank you.